Okay, so now I'm going to describe the actual algorithm for minimizing a DFA. So here's my DFA. It's very similar to the one before, but I've added an extra state here, R1. So the very, very first step you do before even running the algorithm, to make your life easy, you should immediately delete any unreachable states. Because if a state is unreachable, that means it can never affect the behavior of the DFA, and it also means you don't have to correct any transitions that are missing a state. So by inspection, here R1 is an unreachable state because there's no arrows pointing into it. So I can just freely delete it. There we go, now it's gone. Okay, so what we now do is we're going to list all the states in a big group, and by default we're going to assume all the states are equivalent until we can find some evidence to the contrary. Now clearly final and non-final states can't be equivalent because one rejects and one accepts. So by default we list all the non-final states. This is going to be like a list of lists. So all the non-final states, S0, S1, S2, T1, T2, and all the final states, S3, S4. Okay, intuitively we'd expect S3 and S4 to be equivalent because they're two final states really doing the same thing. And we expect T1 and T2 to be equivalent because you could sort of like delete this T1 state and make zeros from S3 and S4 point to T2. They're both trap states, right? So we should expect that these two things are equivalent and these two things are equivalent. But let's see what the algorithm says. So what we do is we pick a character to transition on, to split on. I'm going to pick 0. And we identify states with the equivalence class that they go to. So if two states transition to different equivalence classes, they can't be equivalent, and that means we have to split the groups. So it's a bit hard to describe with the algorithm formally, but if you go through an example, it'll make sense. So let's see where S0 goes to. So there's two groups here. There's the final group and the non-final group. So S0, when you read a 0, goes to S1. That means it goes to a non-final state. So we'll put S0 here. S1 under 0 transitions to T2, which is still a member of this group. So S1 stays. S2 under 0 also goes to T2, so S2 stays. T1 goes to itself. T2 goes to itself under 0. Okay, so no changes there. And under 0, S3 goes to T1 and S4 goes to T1. They both go to the same group. They both go to the same group, namely this group, which means we can't split anything just yet. Because both S3 and S4 act the same. They both go to the same group when reading a 0. So no splits yet. Well, 0 didn't do anything, so let's try 1. Okay. S0 on reading a 1 goes to T2. S1 reading a 1 goes to S2. S2 reading a 1 goes to S3, which means S2 went to the opposite group. So S2 is a non-final state. They went to the other group, which means it can't be equivalent to these states here. So that means you have to put S2 off in a separate group. T1 under a 1 goes to itself, so T1 stays, and similarly T2 stays. Okay, so we identified S2 is different from these guys here. They can't be equivalent. Okay. S3 and S4, well S3 goes to S4 under a 1 and S4 goes to S3 under a 1, so we can't split because they both go to the same group. So it's not important whether they stay in the group, it just matters whether they go to the same group. So before S3 and S4 both went to this group, and here S3 and S4 both went to the same group. So again, we can't split because there's no evidence that they're different. Okay? Now because there's a split, we have to basically run the algorithm again. Whenever you attempt to split on 0 and nothing happens, and attempt to split on 1 and nothing happens, only then can you halt and say, aha, these things must be equivalent. So, and in general, if the alphabet's larger, then you have to keep trying all the combinations. So we managed to have something happen for a split on 1, so we have to start again. So I'll try splitting on 0 again. S0 goes to its group. S1 goes to its group, because S1 goes to T2, and T2 is still in the group. T1 goes to itself, T2 goes to itself, nothing interesting happened there. S2 goes, well, I can't split a singleton, so I can leave that alone. And S3 and S4, we already know that it's split on zeros. Okay, nothing occurred, so let's try 1. S0 under a 1 goes to T2. S1 under a 1 goes to S2, and S2 is no longer a member of this group anymore. That means S1 is different. So we'll put S1 by himself. T1 goes to T1, T2 goes to T2. And we already know S3 and S4 don't split on the 1. Something happens, so we're going to do the algorithm again. Split on a 0, S0 goes to S1, which is no longer a member of this set. So that means we turf S0. So that means S0 is going to have to go in a separate group by itself, because S0 under 0 no longer is a member of this group. It goes over to S1. Okay? T1 goes to itself, T2 goes to itself. Can't split singletons further, so we can just skip these. S3 and S4 both go to T1, they both go to the same place, so no split. So we've got a split on 0, so that means, again, we have to do the algorithm again. So we try split on 0. You have to do a split on a character, as you have to be at some point where doing any split on any character makes no difference, and only then can you terminate. So it is a bit laborious and lengthy, but it always works. T1 and T2 go to themselves, so no change there. Singletons, no change there. And S3 and S4, we already know they both go to the same place, so no change there. Okay, nothing changed. Let's try 1. T1 and T2, they both go to themselves. I can't split singletons. And S3 and S4 both go to each other. Tried splitting on a 0, I tried splitting on a 1, nothing occurred. So the algorithm terminates. And because these two states are in the same group as each other, we can declare T1 equivalent to T2 and S3 equivalent to S4. Okay, so now we can redraw DFA, including only one of each of the equivalent states. So because T1 and T2 are really the same thing, we can leave one out. So I'm going to leave out T1. So we'll leave out T1. And S3 and S4 are equivalent, so we can leave one out. So I'm going to leave out S4. So we can redraw the state diagram. S0, S1, S2, T2. 1, 0, 0. So we're just copying everything that was already there. Okay, and so now here comes the tricky bit. Because we deleted these two states here, that's deleted the states that S3 goes to, right? So how you fill in the remaining arrows is you just send it to an equivalent state. So S3, when it reads a 0, goes to T1, and we know T1's equivalent to T2, so I can just change this arrow to go to T2 instead. So instead of this arrow here, I can make S3 reading a 0 go to T2. Okay, so we'll do that in my new diagram. What other arrows need to be fixed? This arrow here, because if I'm in S3 and I read a 1, I don't know where to go. So S3 under a 1 goes to S4. What state was equivalent to S4? S3 was equivalent to S4. So that means I can take this arrow, instead of S3 going to S4, I'll make S3 go to an equivalent state to S4, namely itself. And there we go. That is my new minimized DFA. And as we can see, this DFA here is exactly the same as this DFA here. So this really must be the minimal DFA for this language, assuming the language for this DFA really is this. I guess you'd have to formally prove that, but assuming that you know the language for this DFA is this language here, then this is the minimal DFA for it. Why is that? Because I picked another DFA with the same language, and I cranked the minimization algorithm, and I got this DFA here. So I know, because the minimization algorithm has spat this out, if I attempt to run minimization on this, nothing will happen, because I basically just get these two bottom steps here. Sorry, I beg your pardon. If I try to run minimization, it'll be basically the same algorithm, but if I was missing T1 and missing S3, and you'll basically split all the states up into singletons. So that means this DFA here truly is the minimal DFA for this language.